Okay, so we're going to start out looking at section 2.5, and we're going to look at what happens if we had the limit as x approaches 4 of x squared minus 16, all that over x minus 4. And we saw whenever a function is continuous, so when a function is continuous, we can use substitution to evaluate the limit. Can use, I spell can, we can use, well, the definition. If a function's continuous, then the limit as x approaches c of the function. So if you want to if you know that f of x is continuous, you want to evaluate the limit as x approaches c, then we can just plug the c in for the x as long as the function is continuous. Now the problem here we could see is if we try to evaluate the function value, 4 squared is 16, 4 minus 4 is 16. This ends up being 0 over 0. So we end up with this problem. This function is not continuous at 0. Sorry, it's not continuous at x equals 4. So this function is not continuous at x equals 4. And actually what this function looks like, we graph it, well, the graph of this function is basically, this looks like a line, starts here at 4. We'll see kind of what the line is in a little bit, but looks kind of like a line, and it has an open circle at 4. So I can't evaluate this by plugging in because I get 0 of the top, 0 of over the bottom. So if I did try to plug in, so if we tried to plug in, so if we try to plug in 4, we get 4 squared minus 16 over 4 minus 4, which is 0 over 0. So that tells me right there is no function value. So this function here is not continuous at 4. The bad side of that is this neat way of evaluating limits by plugging in that only works when the function is continuous. So here's how we kind of get around that. If algebraically we can rearrange this function, we can get where this is the same thing. This coincides with the continuous function everywhere except at a single point. Then we can use the continuous function and plug into the continuous function to evaluate the limit. So what we're going to do with that is we're going to look at, let me bring that on down. So this is kind of the function we're dealing with still. And we can note if we have x squared minus 16 over x minus 4, we can factor the top. This is the difference of squares. So it'll become x plus 4, x plus 4 over x minus 4. Sorry, x plus 4 times x minus 4. X times x is x squared. Minus 4x from the outer plus 4x from the inner. They cancel. And then 4 times negative 4 is negative 16. And we'll see that they cancel. And so this equals x plus 4 for all x, where x is not equal to positive 4. So basically what we're saying is x squared minus 16, all that over x minus 4, this is the same thing as x plus 4. So these two functions look the same everywhere except for at x equals 4. So if you remember, the function's limit doesn't depend on the x value itself. So basically, let's recap what I just said in words, and then we can kind of see what it means. So x squared minus 16 over x minus 4, that is the same as x plus 4 for all x's except x equals 4. So as long as you are an x value that is not equal to 4, so x squared minus 16 over x minus 4, it's the same as x plus 4 for every single x that isn't 4. So as long as you're an x that isn't 4, these two values are the same. And if you remember, the limit doesn't depend on the function value itself. So if we look at what is the limit as x approaches 4 of x squared minus 16 over x minus 4, if we think about the limit of approaching from the right, we'd be using numbers like 4.0001, 4.000001. Those are very close to 4, but they're not 4 itself. So this right here will be the same as just x plus 4. And if we look at approaching this from the left, we're looking at numbers like 3.999, 3.99999. Again, those are very close to 4, but since they're not 4, this right here is the same as that. So this right here is the same as x plus 4 for all x's except for 4. Since the limit never actually takes the value 4 itself, it just looks, what happens is you get close to the 4 from the right and you get close to the 4 from the left. We get that the limit as x equals 4 is the same as the limit as x approaches 4 is equal to the limit as x approaches 4 of the simplified form of that expression. So whenever the limit's approaching 3.999 of this, that's not 4. So this complicated function is the same thing as this easy function. Well, then what we can use is now this complicated function that wasn't continuous, this function here wasn't continuous at 4, we now have it being the same everywhere except for at 4 as the function that is, as this function x plus 4, which is continuous at 4. So we're able to use this function here, the fact that this function is continuous, and we're able to evaluate this one by substitution to get that 8 is the value. When you're going through and working on these, the times that this trick works, where you're able to cancel something out and get this function the same as a continuous function. So like this function here is not continuous at 4, so we can't use continuity to evaluate this. But after we cancel it out, we get that this function here coincides with the second function here, and the second function here is continuous at 4. So that lets us set the limit. And really what's going on is if we look at this right here, or let's say, whoops, sorry. So this one is continuous at 4 and we get 8. If we look at this right here, this point here falls at 8. And basically what's happening is if you look at the left-hand limit of this, it goes here. If you look at the right-hand limit of this, that would approach from there. And the value that would make this continuous is where that missing dot is, which is the value that would be given to us by x plus 4. So basically what's going on is with the removable discontinuity that we have here, you have the line x plus 4 except there's a hole there. And so what we're doing is we're canceling out the part and seeing what's kind of the baseline actually supposed to be. And then we can use that the simplified form after you cancel is continuous, and we can use that continuity to sort of plug the hole to see where the limit actually would fall. Even though in this there is a gap there, remember the limit can still exist even if the function value doesn't. And so we're using the fact that this complicated function is the same as this function for everybody that's not equal to 4. And then we can evaluate this function using continuity. And when we go through and do these, to get these types of stuff might work, we need to verify that f of x has an indeterminate form. So f of x needs to have an indeterminate form at x equals c for this to work, I guess we could say. And types of indeterminate forms are, so what are the forms? What are the actual indeterminate forms? They are 0 over 0, which was the case that we had here. When we tried to initially look at this, and we tried plugging in 4 and kind of seeing what's going on, we ended up with 0 over 0. And we could see that that was still like if x gets very, very close to the 4, the top's approaching 0. As x gets very close to 4 down here, the bottom's approaching 0. So we got the 0 over 0 form. So that's one of the indeterminate forms. You can try these sort of things if you're in forms of infinity over infinity, if you are in forms of infinity times 0, or if you're in forms of infinity minus infinity. All of these cases here, these indeterminate forms, these will lead to types where sometimes we can use these cancel it trick and get it equal to something that, or get it coincide with something that is continuous everywhere except for the value, and then we can use the continuous function to figure out what the limit is. So here we kind of use continuity, like this function here is the same as that function as long as stuff's not 4. And then, since this function is continuous, we can evaluate by substitution on this part when we couldn't evaluate by substitution on that part. Okay.